Hello and welcome to the web series, ZeroPM Pieces. In the ZeroPM Pieces, the researchers in the project will tell you about one piece of the ZeroPM puzzle that they're working on. So without further ado, here comes a ZeroPM piece.
Right, so I think, this is just a brief overview of task 6.1, which is related to environmental fate and exposure modeling as part of the ZeroPM project. And so just to give an overview of the objectives associated with this work package 6.1, which I'm largely responsible for, the objectives are to develop a Fugacity-based model that will include groundwater and has the capability to also handle polar and ionizable organic chemicals with respect to estimating their environmental fate and exposure. Once developed, then the model can be applied to address various case studies within the project, as well as to be used to estimate the exposure concentrations in intake water associated with drinking water, for instance, which enables an evaluation or an estimate of human exposure overall. Basic principles associated with Fugacity modeling. And with an emphasis on sort of talking about this desire to expand the physical-chemical applicability domain to include these more challenging chemicals, polar and ionizable organics, and I'll talk about some of those challenges in this presentation. So in talking about Fugacity, I'm going to assume there's probably a variety of people who have come across this term before, maybe some who haven't. So I'll just start really basic, sort of an overview of what this is. Fugacity is a concept that really fits within the space of thermodynamics. It was introduced by Lewis in 1901 and refers to the escaping tendency of a chemical. And what is nice about Fugacity is that it has units of pressure, and so it lends itself well to sort of a conceptualizing what might be happening within a system. So if you have a closed system, for instance, that may include both water and sediment or soil within it, and you introduce the chemical to the water into that system, what is happening is that the chemical will move to area of high pressure, which is where it initially starts in the water phase, into the soil or sediment, which has a lower pressure until the system reaches an equifugacity or equal pressure throughout the entire system. So as a consequence of this, it's a convenient method for defining when thermodynamic equilibrium occurs. Argument for why Fugacity is useful. The environmental fate and exposure of chemicals in a multimedia environment, because chemicals are going to partition between different media, and they're always moving towards an equilibrium, as we understand within the concepts of thermodynamic. And so knowing the differences in fugacities in the different systems helps us to understand the relative behavior of chemicals in the environment. Following the publication from Mackay in '79 and through the '80s and '90s, the application of Fugacity has found its way into a number of regulatory models and is used quite widely to estimate the exposure of chemicals, such as in Europe. The USIS model relies a lot on these principles that were developed out of this publication. So just sort of continuing on this theme of trying to understand what Fugacity is, as I say, it's at equilibrium. The Fugacity between a soil and water, for instance, will be equal. And so when we have this equal concentrations, or when equilibrium occurs, we can then take the concentrations of the soil and the water, the ratio of this, to derive a soil-water partition coefficient, for instance. This is more commonly referred to as a KD value, and KD, we find, is for a lot of the neutral organics, is largely influenced by the fraction of organic carbon that's in the soil. And so if we know KD, we can derive the organic carbon-water partition coefficient, which becomes a relative term, a very important term for trying to understand the sort of behavior of different organic chemicals in the environment. And so often we refer to KOC more often for organic chemicals than we do for KD. And this is all because we tend to find that the partitioning behavior is dominated by the fraction of organic carbon that would be in the soil. Fugacity is also proportional to concentration, and the proportionality constant in this term is known as Z. And Z is this term we refer to as fugacity capacity. And it's also an important sort of concept that comes into play because it helps us to understand the capacity of a particular media to retain or a chemical substance. So in the example here, where the chemicals for organic chemicals that are partitioning into the organic carbon of the soil, we would find that the soil has a higher fugacity capacity than the water, and so the concentration then in the soil can be greater than the concentration in the water, simply because the fugacity capacity of that system is greater than in the water, although the fugacities are equal. So it's clear that fugacity capacity then is a media-specific term. For many hydrophobic organic chemicals, they tend to concentrate in organic matter that's in the environment, such as octanol. And octanol is really important because we, of course, use KOW quite a lot. And the reason that KOW is important is because the octanol or the fugacity capacity of octanol is much, much greater than the fugacity capacity of water. So again, for hydrophobic organic chemicals, we can use the differences in how chemicals will partition between water and octanol as a way to understand how they might interact with different types of organic material in the environment, such as lipids and biological organisms, but also in terms of organic carbon and soils. And we are aware that a lot of algorithms have been derived to estimate KOC based on our understanding of KOW. So there's this relationship that exists between KOW, KD, and KOC, all because of this partitioning behavior of chemicals between different systems. Now, another component of this, which doesn't get talked a lot about, but I think may actually have some importance in some of the work moving forward, is sort of this appreciation that concentration is a system-dependent property. So it depends on the mass and the volume of the system that we're working with. So while the fugacity capacity is a constant term, for instance, for soils, if the volume of the soil in the system that we might be looking at, for instance, or the octanol in the system decreases significantly, then we might actually find that the concentration in the water would be much greater than the fugacity or the concentration in the octanol, although the fugacity capacities haven't changed. And so the volume ratios can play a really important role in influencing how chemicals or the fraction of chemical that might be found in different types of media. And I think this is important when we start to look at environmental media, because there are big differences in terms of looking at a saturated zone in groundwater, for instance, versus what might be occurring in surface waters. So while this is well understood for neutral organic chemicals, things get a little bit more complicated when we start to consider ionizable organics. And one way to think about this is if we look at that octanol water system, for instance, and we have an ionizable chemical. Given if the pKa of the chemical is within the pH of the water in that system, there will be an equilibrium that occurs between the neutral species of the chemical and its ionized form. As a result of that, there will be a number of different types of equilibria that will establish between the water and the octanol, as well as between the different forms of the chemical that can exist. This leads to potentially a complex sort of system that's occurring within the octanol water measurements that we might be making. And to correct for this, a lot of people will refer to DOW, which is meant to sort of capture what is happening in the overall system that we're looking at. Now, when we refer to DOW, it is important also then to reflect on what the pH of the system that you're talking about, because DOW then can potentially change from one pH to another depending on what the pKa of the substance is. And pKa is here, of course, describing the acid dissociation constant of the chemical and how it behaves under different pH scenarios. So recognizing this is important, particularly when we start to look at chemicals that are used in commerce. And this has been known for quite a number of years now. There was a publication from Franco et al., for instance, in 2010, where they looked at the chemicals that were registered under REACH, and they found that nearly 50% of these chemicals were actually ionizable. with 27% being acids and 14% bases. If we dig a little bit deeper and we actually look at a specific group of chemicals, such as the active pharmaceutical ingredients, we see, which is an important group of chemicals because we know that they're biologically active, we find that 80% of these chemicals are ionizable, with 75% being bases and 20% acids. Now, the reason I'm sort of reflecting on this is sort of just commenting on the fact that we have this sort of differences in terms of distribution of acids and bases, and reflecting on whether or not a chemical is potentially an acid or a base is important because the properties of these chemicals can lead to significant differences in how they might interact or sorb to different types of surfaces in the environment. So to sort of illustrate this, there's sort of an understanding that we have that if you have a base in the environment, as it becomes more speciated, it will tend to create a positively charged cation in the environment. And this positively charged cation will sorb more strongly to a higher extent, or the Kd value will be greater than the neutral form. And this is largely because there are a lot of negatively charged surfaces in the environment, which increases the degree of electronic interactions that can take place. And so we will tend to see higher sorption capacity for bases relative to the neutral chemical. For acids, which will form a negatively charged anion when they become speciated in the environment, the partitioning or the Kd value will tend to be less than what it is for the neutral form. And this is because the electronic interactions will be more repulsive. And so the sorptive capability of these chemicals will tend to be more dominated by non-specific interactions of the molecule, depending on what the structure of the molecule is. And it may behave more similar to the neutral form, whereas this difference for the bases becomes potentially more significant. So understanding whether or not you have an acid or a base, and if it's in a speciated form in the environment, is important because it has implications in terms of how these chemicals are going to sorb. So as I said, this is somewhat well understood. There is this work, of course, that was done by Stevens-Roga and Kai Vegas, where they sort of measured or looked at differences between measured Kd values for a group of amines, and what they found, differences in terms of primary, secondary, tertiary, and quaternary amines for different types of soils. So we have two soils here, one soil which has a very high organic carbon content, a relatively low clay content, and the other reverse, where the organic carbon content is low and the clay content is high. And they see a significant difference in sorption behavior for these chemicals between these two different types of soils. And this is largely driven, that they argue, in relation to the cation exchange capacity of the clay in the system. And so as opposed to sort of deriving an algorithm that's based on, for KOC, that would be based on the fraction of organic carbon entirely, what they have derived is a relationship based on the cation exchange capacity of the system. And this is meant to try to address then this very specific electronic interaction that is occurring between the molecule and the surface, the substrates that they are interacting with. Conversely, we do have some work from Melanie Kaw during her PhD with Colin Brown that was published way back in 2007, where they looked at some pesticides, which are typically dominated by acids. And when they looked at the relationships of Kd for this group of chemicals which are speciating in the environment, they find a relationship is more strongly influenced by the organic carbon content in the soils. And so they can derive then a log Kd value that is related then to a corrected log KOW value, in this case log D, and the organic carbon that would be in the system. And so in this way that they're sort of arguing that when you account for the difference in partitioning behavior of the chemical, you are able to still derive a relationship with KOC in an efficient way. So there's this difference then that seems to be important when we're thinking about whether or not a chemical is an acid or a base. That is relevant to try to consider when developing a model. So all of this really then requires us to think very closely what's happening at this microscopic scale. How are chemicals then interacting with the soils that they're coming into contact with, and how does that then influence on the freely dissolved concentration? So here we really do have to have an appreciation of the geology that's at play in terms of the soils, but also in terms of understanding the chemical, its structure, its pKa, and the pH of the system. And This is needed because we want to be able to derive this free concentration in the system, because that is what would represent our concentration in the water that would be taken up as drinking water moving forward. And so all of this then has implications on how we then derive and utilize measures or estimates of KOC within the multimedia modeling environment that we're need to try to move forward. So does all this matter? I think I'm trying to make a case that it matters quite a lot, and it's really important to understand the potential for an organic chemical to speciate when it's released to the environment, because it's important to understand this as it reflects a need to sort of quantify and characterize how this influences on exposure. So we do know that speciation can influence exposure, but it can also potentially influence on adverse effects. And so since the goal of the overall work package 6 is aimed at trying to evaluate risk, we need to have an understanding of the relationship then of how chemicals, this speciation behavior, and how it influences on the freely dissolved concentration as it influences on exposure. And that's sort of the key element that I'm most interested in moving forward. So the implications then are really all surrounding and how this might impact on KOC. We have a number of linear regressions that are proposed for estimating KOC based on KOW, which also can have been proposed to extend to DOW. There are differences in behavior, however, between acids and bases that should be taken into account, and understanding how the interactions occur between different types of surfaces. Of course, all of this would benefit from having more direct measurements of KD and how that could be extrapolated to KOC as sort of as an input into the models that we're using. And so moving that forward would be, of course, beneficial. Now, within the TGD, there is some guidance for estimating different KOC values, and these are various QSARs that have been proposed, and we do have some that are relevant for some of the chemical groups that we're looking at within this project, such as the triazenes, triazoles, and sort of a question to sort of to really scrutinize very closely the effectiveness of these regressions to handle the types of chemicals that we are looking at. Now, all of this is important because a number of different tools have been developed and modified in Fugacity's modeling space, and there have been a number of approaches that have tried to modify them to account for ionizable polar chemicals, and most notable amongst those, I'm just going to draw attention to some work that was done by Antonio Franco as part of his PhD in a publication led by Stefan Trapp in 2010, where they sort of applied the different algorithms for KOC and tried to investigate differences between the acids and bases, and in this context and towards developing a multimedia fate model, which would then account for how chemicals would change their partitioning behavior depending on the pH of the system relative to the pK that exists. So I found this very interesting a number of years ago, and I did some work as part of an ESOTOP task force where I took the model from Stefan Trapp that was proposed and sort of ran this through a chemical space approach. And the reason that I like the chemical space approach is because it lends itself to trying to evaluate how some of the assumptions within the model might influence on overall environmental fate. And so in running this forward, what I've done is sort of taken this approach where you can take hypothetical chemicals on a 1 by 1 degree log or a 1 by 1 degree log scale units of log KOW and log KW. You vary these and you use these as input parameters into the model, and then you can pull out of this sort of some information such as the changes in how the chemical will be moved between the different compartments. So we can map out, for instance, the fraction of chemical that would be in the water, the fraction that's in sediment, and the fraction in air relative to the KOW and KAW of the chemical that you're looking at. Now, for ionizable chemicals, we can then start to look at how these changes might reflect on differences in pH, but also in terms of pKa, and then we can have a bigger understanding of the overall behavior of these chemicals within this model environment and how the assumptions then play out. So I've done this for the acids, and so we can see for this group of chemicals that as the chemical becomes more speciated in the environment, that its environmental fate is largely going to, or the fraction of the chemical will largely be associated with the aqueous phase, whereas the neutral species is behaving, as the neutral species becomes more predictable in terms of how it might behave. There's a few benzotriazoles that we have in our list of chemicals that we're looking at, so I've just mapped them into the space. They have pKa's around 9. As acids, and you can see that their behavior in the environment in this case would behave similar to the neutral form of the chemical, and in this case it may not necessarily be important to sort of take these chemicals or the differences in partitioning behavior into consideration relative to the speciated form. But what's nice about this is if we can begin to expand our understanding of how chemicals with different properties might behave in the environment. And of course, the PFAS have pKa's that are less than 4, and so their presence or the fraction of these chemicals will be largely associated with the aqueous phase using this KOC-based approach. For the bases, on the other hand, we see a shift or a slightly different sort of behavior that's occurring. So as the cation becomes more present in the environment, we see actually more absorption that's occurring relative to pKa and the pH of the system than it is for the neutral form of the chemical. And in this case, I've put in melamine, which has a pKa of 5, and of course, its behavior is not so much different from its neutral form in this instance, but again, having the ability to look across all of the chemical space allows us an opportunity to try to better understand what might happen for different types of chemicals as we go through this space. So the implications of this, of course, are all relate to our ability to correlate the KOW that we might be looking at with KOC, and the implications are whether or not KOC is actually the most relevant metric to use in trying to understand the sorption behavior of the chemical. It might be relevant for some of the acids that we're looking at, but I think it really comes into question when we start looking at cations, which have pKa with an environmentally relevant pH in the environment. I didn't go into a lot of discussion on the influence that the molecular structure of the chemical can have, but obviously the surface charge area of a cation, for instance, can change its sorption behavior, and it may be that the non-specific interactions may become more important than, for instance, the electronic interaction that might play out. So all of this becomes important to sort of really scrutinize moving forward, and raises questions around the relevance of octanol for some of the ionizable chemicals that we might be looking at. In some instances, it might be appropriate, in others it may not. So the bases, I think, really represent the more challenging group of chemicals, particularly when considering KOC, and so there's a need to better understand, particularly this group of substances, and how to predict, for instance, sorption to sludge is also sort of a question that is important to understand, because if we have application of biosolids where these chemicals might be sorbing to, it's again trying to better understand the interactions that may occur with sludge, which may be different than with different types of soils. Interesting enough, some of what I've been talking about is also sort of expressed in a recent Acetoc Task Force report and a publication that was led by Sasha Balowski, where they also raise a number of these sort of concerns around the use of KOC in this context, and sort of argue for perhaps a more broader or holistic way of trying to think about how these chemicals partition in the environment, and maybe KD, the KD itself is sort of plays into the role. So with that, I'm done, and with the presentation, and happy to address questions if there are any.
ZeroPM, Zero Pollution of Persistent and Mobile Substances. This project has received funding from the European Union's Horizon 2020 Research and Innovation Programme under Grant Agreement number 101036756.